find some help. What kind of tools you can use for post-processing, pre-processing, visualization. We'll discuss all of this. And then we'll go through hopefully some more difficult runs. For instance, the Vortex code that we talked about this morning, Olaf. And then if you want to do Campbell diagrams and linearization, how do you do this? We have new tools to do this, so we'll try to also give you a tutorial for this. And so if you are bored at any point in this presentation, because if you're already a user and you already know how to run OpenFAST, you can go to the slides that is in this tiny URL. You'll find my slides. And at the very end, you'll find the appendix. And there's a couple of challenges for you. There's one in particular, one challenge in particular, which is about Luigi and a pole. So it's not even a wind turbine. So you'd go around here, for instance, and you'll find in the package that you download, there's a zip file on this tiny URL. And basically, this is the folder you'll download, package, OpenFAST, and you'll have some folders in it and simulations. Those are going to be a couple of the cases we're going to run. For the advanced users, you can try this debugging challenge if you want, or you can go into the other slides where there's some more small challenges you can do with your text editor, operating system, and OpenFAST features. Okay, but first I'm going to go for all the users that are beginners. I'm going to go through the regular presentation. It's not great. Yep, thank you, Jason. So yeah, an overview of the tool. I think Jason already gave you an overview, but we have those big executables. OpenFAST is one big executable, and that's usually what we call a glue code, the OpenFAST glue code, because it glues all the modules together. And then we have some driver executable. If you just want to run aerodynamic simulation, hydrodynamic simulation, then we have smaller executable that we call drivers. And then there's some DLLs, in particular, if you want to have a controller. If you want to model your controller, you're going to need a DLL. And typically, we use nowadays the Rosco controller, so it's the Rosco DLL. We won't talk too much about Rosco today. But so the executable you can find in the package, and there's a folder called binaries, and then you can download the binaries for OpenFAST. I'll get to it. And then once we run simulation, we're going to be able to usually we want to visualize things. So some of the tools we'll cover is ParaView, like Jason mentioned, PyDatView, and ACDC, which is for Campbell diagrams. And then if you want to get your hands really dirty, then you get into programming. So today I'll give you some MATLAB and Python, very small scripts. So if you want either MATLAB or Python, you can use both. There's a switch at NREL. We tend to use more and more Python. So it's maybe in the long run, if you plan to use OpenFAST, it's not a bad idea to go into Python. Anyway, so to get you started, it's, as Jason showed, at the high level, the system takes some inputs and produce some outputs. And the main input that the executable takes is a bunch of files, okay, a bunch of input files for OpenFAST. The main one has the extension .fst. It's a convention, but we use the extension .fst for the main file of OpenFAST. And what happens is this file doesn't have all the information, but it actually refers to other files. So because OpenFAST has a lot of modules, each module has its own input file. So that's something that maybe new users can find a bit confusing. So not only do you have one file, the main.fst, but you're going to have a lot of files that are referenced by every files. So you'll have other subfiles that are referenced in this file. So you'll take the basic idea is you take this main.fst, you give it to the OpenFAST executable. It's a terminal application, so you have to run this in the terminal, and then you get some outputs. Those outputs are going to be, so the input files are going to be the parameters of your turbine. How big is your turbine? What is the weight? What is the mass of the different component? What is the wind speed, etc. In terms of output, the main output we usually look at is has extension .out or .outb, and that's going to be a time series of different signals that you can imagine for a wind turbine. So one output could be the wind speed, even though that's also an input. But you can have a time series of the displacement of the tower, the displacement of the blade, the acceleration of different part of the structure, or typically the forces. What are the forces at the bottom of the tower? So those you're going to see time series. Those are going to be stored in this .out file. And then if you do visualization, you're going to have .vtk files. If you do linearization, .lin files, etc. The main one we're going to talk about is usually a time series of output. So in practice, how does that look like? Well, in a given directory, you could even try, if you have the package in front of you, you can, under simulation, you can go under case number 2, and it's going to look something like this. As I mentioned, you're going to have a main file, .fst. You don't have to call it main, but I do like to call it main. And the output file is going to be main.out. That's automatically, once you run OpenFAST, OpenFAST is going to call it with the same file name that your FST file. This is an example of a main.fst file. And so that's what I was telling you. If you look, the blue boxes that I highlighted, this is the Elastodyne file, then the inflow file, inflow wind file, and the aerodyne.dat file. So those are other files that specify, for instance, this is the aerodyne file. So those are text files. It's overwhelming as a new user because there's a lot of input going on. But you get used to it, and there's good documentation for them. But so this is now the aerodyne file that I opened, which has many lines, and it's going to define, what are the options for the blade element momentum theory, the aerodynamics. But you're going to also need new files to specify what is the chord of my blade, what is the twist of my blade. Those are aerodynamic data that are pretty interesting for us to do the calculations. And also, at each cross-section of your blade, what is the airfoil data, so the lift and the drag coefficients of your blade. So this is aerodynamic data. So you're going to have to define in this file where are those defined. Give me a second to get the pointer. So for instance, the polar data here, in that case, I just have one polar data. That's a bit uncommon. Usually for a blade, we would have sometimes either 10 polars or like even 50 polars. So those define the lift and drag coefficients. In this example, only one polar. And this is an example of output file. When it's in a text file, it's basically different columns. The first column is the time, and then the other column is like, I can see wind. Those vocabulary is a bit hard, but wind 1 vel x, that's the wind speed at a given point in the x direction. You might find the out of plane deflection as well. And so we'll run this test case, and you'll be able to open this file and see that you get this kind of outputs, and we'll be able to plot them to see what they look like. Some small notes. You can use absolute file names when you do this, when you reference files within a file. You can use absolute or relative file names. I recommend using / because it depends on which system you are. Windows allows for both, but try to avoid using spaces. I mean, OpenFAST works with spaces in your file names, but you need to put quotes around them. Don't forget the quotes. Yeah, OpenFAST will overwrite output files. So if you made a very long simulation, try to back up your results. That's it. So how do you get OpenFAST? There's some we have this presentation we shared with you, so it has a lot of content in it. It's probably overwhelming right now because there's a lot of information. But the idea is like you can go back to it later if you need help. Hopefully you have all the links. So we document on our documentation how to install OpenFAST. If you're using Windows, the easiest is to download from GitHub the executable. So you would go on this GitHub page with the /releases to see the different release of OpenFAST. And if you click under assets, you can find different executable, and then you can download the one you want, which is usually OpenFAST 64.exe. But if you want to run FastFarm, you'll find FastFarm as well, and TerpSim and the Aerodyne driver is going to be there as well. If you have a different platform, hopefully you're more versed about the terminal, and you'll figure out how to install it. You can even compile it if you are a programmer, an advanced user. To really run OpenFAST, it's a command line program, so typically we're going to need to use a terminal. Open a terminal. I'll show you how I do it on Windows. Hopefully you know how to do it in your system, but feel free to ask if you don't. And then you need to navigate to a given folder. So this is where it's always a bit tricky. You might have this executable, OpenFAST exe, and then you have your main.fst. My first recommendation would be like copy paste your executable next to your file. When you're a beginner user, that's the easiest you can do. Okay, you take the executable, you put it in the directory next to your main.fst, and then it's pretty easy to run it. But once you have a terminal, the terminal might not be in this folder, so you need to do cd for change directory. And then you go to this folder where you have this input file and the executable. Once you're in there, you just you do openfast.exe and the main input file, and OpenFAST will run. And it will show, it's in the terminal. Your terminal might be black or white. It's going to show you something like this, and hopefully at the end, it tells you that it ran. It might give you some warning, so it's very important to read what OpenFAST tells you. So this is my command here, OpenFAST main.fst. We have a bit of a banner at first. Then what's interesting is OpenFAST is going to tell you the version that it's running. So when you need help, always pay attention to this version, because the developers, or for us to help you, we need to know what version you're using, on which system and things like this. And it might give you some warning or some errors. So always try to read what's going on towards the end, because that can help you figure out if you made a user input error, you'll figure this out here. Or if everything goes well, it's going to tell you OpenFAST finished normally. So we'll try this together. But before we do that, some notes. Like I said, the easiest is to take the executable and put it next to your FST file. But you don't have to. You could put the absolute path of the executable. That's my first example on the left. So that's an absolute path to the OpenFAST executable, and then the main.fst. Or you can even use a relative path to your executable and then the main.fst. You can do the opposite. So you can be in the folder where the executable is, and you can go get any kind of FST file with a relative path or an absolute path. Okay. You'll find whatever works for you. One thing you can do also, which makes things easier, is to define what we call an alias. Who knows what an alias is? Raise your hand if you know what an alias is. Not enough people, but that's okay. So this is one of the challenges if you want, and I think I'll tell you how to do it on Windows and Linux. It's really a way to call any executable from anywhere you are in your terminal. So it's very useful for OpenFAST, because the OpenFAST executable is quite big, and if you have to copy paste to all of your folder, sometimes it could be annoying. So you could put an alias in your command line window, and then you can just basically call OpenFAST from everywhere. It makes it available to anywhere you are, and with a short nickname. In that case, I use the nickname OF32 for OpenFAST 3.2, and then I can just call it with my input file anywhere I am. More recommendation. So the input file, before we dive into it, typically has a syntax that is always the same. Even though it looks overwhelming, it looks something like this. You have on the left, you have the value. In the middle, you have what I call a key, which is basically the name of the variable that this represents, and then some comments. So as a new user, you'll probably want to read the comment a lot. There's a lot of information. Sometimes those lines get very long, but it tells you enough things. So for instance, the first one, the comment is pretty small. The total runtime, That's how long your simulation is going to be, your OpenFAST simulation. So if you wanted to do a 10-minute simulation, you'd put 600 seconds. You can see that it's in second. You have the unit at the end. A lot of flags of OpenFAST are also like kind of switch between modules, or like 0 means something, 1 means something else. So we call them switches. We use that a lot. So here, if comp hydro is 0, we don't do hydrodynamics. If comp hydro is 1, we're going to use hydrodynamics. So all of this you can read in the comments. So that's something you might want to do as a beginner, is to go through the main.fst and read every single comment. It takes a bit of time, but you'll realize that it's understandable. And yeah, that's probably all you have to do to know about the syntax. Obviously, we wrote better documentation than this, right? The comment is just to help you out as a user, quick, and when you need something quick and dirty. But if you need to know the full meaning of an input, we documented every single input in the documentation. So you can search for this name and you'll find the description of it and some recommendation on how to use it. The input file of OpenFAST, what's important is the order of those inputs. Okay, something to know is if you swap 2 lines, OpenFAST is likely going to report an error. Okay, it is a frustration for new users. We'll try maybe one day to lift this, but at the moment, this is the way it is. And what could be more frustrating is when we introduce a new version of OpenFAST, we might add new lines to the input file. So that's a big bummer. Exactly. I see people laughing and smiling. It is very annoying and frustrating. As I myself, I'm the first one, especially when I was working at NREL, I would use, 20 different versions of OpenFAST because I would debug different things. So I would need input files for different versions of OpenFAST. Anyway, I'll cover this later after the tutorial, I think. I mentioned the output file, this .out. How do you decide what you're going to put in this out file? So you'll see most of the modules, as Jason mentioned, they have a list of outputs. Aerodyne outputs the loads, the aerodynamic loads, for instance, the power, the thrust force, or even the power coefficient. So there's somewhere in your aerodyne input file, you're going to find something called out list, which is the output list. And those will, behind the output list, you'll see you decide as a user what kind of output I want. If you put 0, if you put nothing here, you won't get any aerodynamic output. But in that case, I have 4 outputs, which is power, CP, CQ, CT, so power coefficient, torque coefficient, and thrust coefficient. And you'll be able to see when we open the output file, we'll be able to see a time series of the power because we put those lines in the aerodyne input file. Similar principle for Elastodyne, you can have also some, there's also a power that is from Elastodyne that is different from the power from Aerodyne because Aerodyne only has aerodynamic forces, whereas Elastodyne knows about aerodynamics, but also structural dynamics. If you have any kind of inertial effect, if you have gravity, that's going to add some forces to your system that Aerodyne doesn't know, but Elastodyne knows about. So something also users can be confused at the beginning is you have the power from Elastodyne and the power from Aerodyne, and they are different. Well, that's because Aerodyne doesn't know about gravity, inertia, things like this. It's just the force from the aerodynamics. Something that you might find useful is sometimes we want to know at every single node of our system, for instance, along the blade, you want to know what is the force or the wind speed at every location along the blade. We have what we call nodal outputs. So that's at the very end of your input files for Aerodyne and Elastodyne. You'll find a nodal output section, and it's the same principle here. I just say CL. That means I want the lift coefficient as function of time for every blade nodes. And on the Elastodyne side, I want the bending moment in the Y direction at every cross section of the beam. It's pretty useful. If you want to know all the outputs available, you have to download this Excel file, and I give you the reference here. And yeah, you'll find it on GitHub, and it's a very big document, but you'll find all the output channels that you're looking for. Any questions before at this stage? Is it Yeah. Yeah, go ahead. No. So the output is always going to be next to your .fst file. Yeah. And yeah, that's just the way it is. Some drivers would allow you to do it, but OpenFAST won't. Yeah. So typically what happens is you run different simulations for different parameters. So you're gonna have to have different main file anyway. So your file name for your .fst is going to be different for all of your simulation. So your output file will be next to your simulation or next to your .fst. Another question? Yeah. Yeah, so I'll show you different ways to read those output files. I personally, so there's the text file, so you can it's not difficult to read those text files. You can almost copy paste them to Excel, or you can read them with Python, MATLAB. Or usually we use binary files because when you start to do long simulations, your files get pretty big, and you don't want to have ASCII text files. So binary files, you're going to need an external tool to read them, and we'll go through them. I'll give you examples today. Another question? So errors, user errors are common. That's just a good example. There you go. You just die out. So it's okay to make errors. It's gonna happen. Typically, OpenFAST is gonna tell you you're gonna see this message. As a user of OpenFAST, you're gonna see something like this, aborting OpenFAST at the very end. And above, you go one line up. It says OpenFAST encountered an error, and then you read one line up. So don't be lazy and try to read as much as possible, because it tells you something. It tells you what happened. It's not always super useful, but we try to make our error as comprehensive as possible. In that case, it usually starts with the address in the code where it basically failed, which could be a bit hard to read for new users, but you can see it's fast initialize all and then ed init, which is elastodyne init. So initialization of elastodyne, ed read input. Okay, it's elastodyne reading some input. Read primary file. Okay, open fast input. And then we finally, at the last column, we get the input, the error message, which is the input file elsatodyne was not found. Okay, you can guess what happened. The user made a misspelling. The file is probably called elastodyne instead of elsatodyne. That happens. That happens a lot, more than you would think. So as much as possible, read those error messages. You might find another one like invalid numerical input for file main.fst while trying to read tmax. Most likely that means either you put something wrong into the variable tmax, or you're reading another file. You're making a mistake. The main.fst is not what you think. I wrote some hints for troubleshooting OpenFAST simulations. Some general guidelines for you is if it's not one of those easy errors, if it's more like a physical error, like you think everything should run, but OpenFAST crashes, the numerics appear wrong, like you have a tower strike or something like this. You don't expect this. The advice is to always simplify your model to the minimum. So OpenFAST is complicated. It has many modules. So maybe you don't need hydrodynamics. If your model is crashing, you don't understand what. If it doesn't even run 2 seconds and it crashes, remove the hydrodynamics, remove the mooring system, clamp your tower at the bottom in Elastodyne, make the structure rigid, for instance. So then you only have the aerodynamics at the end of the day. And if it still crashes, or you might have the controller, turn off the controller. So this is the step-by-step approach that can really help you out to figure out what's wrong with your model. Maybe the other way around, you can go when you start a new model, you can start step by step. First, you do the aerodynamics, then you start adding some degrees of freedom of elastodyne. Don't do everything at once, right? It's gonna crash on you. It's very hard to do an OpenFAST model from scratch. So go step by step. And then another error that is common is the second one. Make sure your input files match the OpenFAST version you are using. Like I said, we add lines to the OpenFAST input files once in a while, so you might find errors and I'll show you how to deal with this. Okay, that's what I wanted to go through before we try it, at least. Any more questions? Okay, let's just try. So obviously you have different kind of levels. If you can unzip the package.zip and go to the simulation folder, make sure you have the OpenFAST executable that is also provided. And we're going to try to run it. What we're going to try to run is the NREL 5 megawatt, which is a simple wind turbine that Jason has designed during his PhD. It's a fictitious turbine, 5 megawatts, hub height 90 meters, rotor 126 meters, rated rotor speed of 12.1 RPM. And the first case we're going to run is just going to be an onshore turbine with no aerodynamics. Why not? OpenFAST can do this. We have all kind of modules. Let's just turn off the wind speed. We just have a structure that can oscillate. So it's just structural dynamics with gravity. And we're going to, at the beginning, the tower is going to be moved by 3 meters, and then it's going to oscillate a bit like Jason mentioned. It's almost like a 1 degree of freedom system. So this is what you would do from the terminal. And I think I'm just going to go and help you out. At the end, you can run the Python script to, I have a MATLAB script as well, but either Python or MATLAB to just display the results, and you should see something like this. Okay, that's it. Let's just try for now. I think Jason probably is going to help me out. Power. Yeah, that's okay. So we have yes, that's what they yeah, we're any possibilities for that interesting. Yeah, you almost yeah, there's time for opposites. Go big say it, okay. You say it, look like you, yeah, I got it. You always have it, and so you managed to run it. Okay. Sounds good. Can you try the pipe through? Yeah. Thanks for you. Sure. Take me to the one of the turbine set of yeah, that's okay. Okay, that's just warning, but yeah, check it. What they should I? And the aerodynamics, the yaw angle is good. The yaw angle, that's why so but on the option, but then yeah, it's usually happens for especially in these years. And then you take this, you say, yeah, okay, now you need to open it down and you can right click. Right click and open it down folder.
Yeah, I hear. Yeah. I'll have this scripted map created and work. Yeah, it's probably great. That's like another thing. Yeah, right, where's the X? So it's big. Yeah, you can put that, yeah. That's yeah, I put it. It's actually great thing. Oh, okay. Yeah, that's big. Yeah. I'm learning. Yeah, sorry. Yeah, we can cope with this. Oh, that's why I was thinking of something. Firstly, we that was like it is. Yeah, exactly. But now we check it. Doesn't know. Oh, yeah, okay. We should sort out. Yeah. Yeah, 5 more minutes and then we have organic levels here. One more question. Sarah, but that's one of the stage positive. Yeah, exactly. Then exposed. So they asked me to go down and say, hey, depending on your person, then they but yeah. And I think you don't have them. Yeah. It's so. There's something else. Say, hey, but it's not. It's not. It's not. That's okay. Thank you. That's really good. So, it's kind of you not Linux. Yeah, can you go on the show? See, then you can make good. This is very. So, finally, not Linux. Use this stress. I've been. I don't like that's just a concept. Farmers, yeah. That is the next one I'm thinking. Yeah, so that's probably. And seriously. Yeah, but you can keep them right. Okay. Yeah. Here. You see, okay. So you're getting complete. It's not. Yeah. No, the opportunity is still. Oh, nice. You're putting us on top. Okay. Thank you. Yeah, that's what I think I should. Yeah. So, yeah, if you want, if you have mathematics, you can have. Oh, okay. You can have, yeah, it's method. All right. Good. Okay, I think let's just say some first. All right.
All right, maybe I should have done it in front of you as well, but a couple of notes. I see that's just geeky stuff, but I see a lot of you don't show extensions on Windows. What you can do is you go here, you do options, view, and then there's an option that says show hide extension for non-file tabs. I highly recommend to uncheck that box. You go on view options and then you uncheck the box hide extension for non-file extension, because then you can see what is an executable, what is what. It's pretty important. But yeah, what you had to do is like take this executable, put it into the simulation folder, one. And again, it's pretty easy to open a terminal on Windows. You right click, you do open a terminal here. If you have an older version of Windows, you do file. I don't even have this. You do file and open PowerShell here. Once you have the terminal, you can just do OpenFAST. So I usually tab works. I don't know what's going on. OpenFAST. You don't need to type the first thing. You just type a few letters and then tab, and you have auto completion. Then for main, it's the same. I just type capital M and then tab, and it completes the file name. That's the same for Linux and Mac as well. And at the end of the day, that should, OpenFAST should run. What's very important is what is the version we're running. Because some of you already had OpenFAST, but if you don't have version 3.5, most likely this case is going to fail. In that case, it's run no problem. And we have an output file main.out that was generated by the simulation. You can try to open it with your favorite text editor. And it's just similar to what I was showing you, just a text file with a bunch of columns. And the Python script that I provide can read this. It's a very simple Python script. No, how did I call it? Post-process. What it does is open this main file, this main.out, and it's plotting this those different channels, that's what the Python script does. The first channel is the out of plane deflection. So that's actually the blade flapping. The second one is the in plane deflection. So that's the blade, it's for blade 1. That's the in plane motion in meter of the first blade. Then you have the tower top displacement, TTD, TT disp, fore aft. So those kind of vocabulary take a while to figure it out. Right now it's just a bunch of letters for you, but if you were to go to this Excel spreadsheet I mentioned earlier, you could find that what this means. Okay, this means tower top displacement in the fore aft direction. And the other one is the side direction. And if you remember, I was telling you this simulation is for a case where I start the turbine with 3 meters of tower deflection. So that's why it starts at approximately 3 here. And then the tower goes back and forth. And it decays a tiny bit because there's some damping in the tower. And as the tower is moving, the blades are also flapping. And so that's this simple simulation here. What I would do, so in the binaries, I give you a link to PyDatView. You could try to install it. And what you can do is you can launch PyDatView and drag and drop your output file in it. And that's basically, you can redo the same kind of plot that I was just doing. That's basically the same thing. So you don't have to program it. If you want to debug quickly, that's why I use PyDatView a lot. You can open the output files and debug right away. Any big questions about this so far? Read the basics. Like I said, it's easier if you put the OpenFAST executable next to you. If you know how to do alias, you can put I think I did OpenFAST 35 as an alias, and then you can run OpenFAST from anywhere, which is quite convenient. But yeah, that's kind of one of the challenge for the advanced users is how to do an alias. So, and you noticed in the input in the folder that we only had main.fst, we only had Elastodyne. That's basically the 2 files we needed for this simulation. So the next case you can try to run is case number 2. My laptop is crashing. As case number 2, this time we add some wind. So you can try, now that you know how to do this, I'm going to go faster now, but you can try to navigate to folder number 2, try to redo the same thing, run OpenFAST, try to run the post-processing script, either Python or MATLAB, and you should get a plot that looks like this. What's interesting about this case is I have some nodal outputs. So the easiest is probably for me to show you. So I go package number 2. One thing, again, for advanced users, something you should be able to do is compare 2 folders. You take 2 folders, you right click, you can, whatever you do, but you can compare them. Sorry, I screwed up. We open them in the software to compare them. And this is an example. On Windows, I use WinMerge. I forgot what I used to use on Linux, but it's very useful when you run a bunch of OpenFAST simulation to be able to compare input files and folders. So this is the comparison of folder 1 and 2, and I can look at this main.fst from side to side and see what changed from one simulation to the next between case 1 and case 2. Let me just not show the spaces. So that's it. The only difference between case 1 and case 2 are the one that is highlighted by this program. So very useful if you use Windows. I highly recommend WinMerge. And so the difference we see is simulation 2 has comp inflow equals to 1 and comp aero equals to 2 instead of 0. Before we had 0 wind and aerodynamics. Comp aero equals to 2 means aerodyne 15. We had aerodyne 14 before. Now we're going to discontinue aerodyne 14, but I guess we're going to keep comp aero equals 2. I guess so. I actually didn't even think about it, but yeah. So, and you can see the other differences. Of course, now that we have InflowIn and Aerodyne, we have those input files here. So Aerodis because, sneaky, nice. Yeah, that makes sense. Yeah, okay. But so most likely you'll do compare equals to most of the time when you want aerodynamics. So you can see I have more files here. I have the aerodyne input file. I have the blade definition that's going to give me the chord and the twist. I have the polar, which is the CLCD. And once again, this is where PyDatView is not bad because you can open those files, you can drag and drop them into PyDatView. That's the blade file. And you can see the chord distribution as function of radius, the twist distribution as function of radius. So pretty useful. The polar data, the same principle. You can drag and drop it. This is the CL as function of angle of attack, CLCD, CM. And it's sometimes PyDatView gives you some extra information for advanced users regarding the dynamic stall. It's good to know if you're unsteady. When you use unsteady aerodynamics, you want to know that the parameters you give to OpenFAST are kind of okay. In that case, actually, you can see how it's not fully okay. What do I mean by this? The potential CN is far from the lift. It should be. It has the right slope, but it looks like the angle of zero slope is not the right one. Those two should match. Actually, now I need to go back. I never checked, but you can see how those kind of checks are very important as an advanced users. You need to know. You need to make sure that your airfoil data is okay. Otherwise, the simulation is going to look weird. In this example, I don't think it's okay. So actually, it's a good example. Anyway, so you could run the simulation, get the output file, and run it in. You can open it in PyDatView, and I forgot which signals I'm looking at. But for instance, the tower displacement for aft is looking like this. My guess is since we have aerodynamics, we might have some power in this case. So we starts to be more interesting of a simulation. Okay. In the slides, I show out of plane deflection, tower displacement fore aft, and aerodynamic power. Again, yeah, so you would need to dive into aerodyne. For instance, you could open the aerodyne file and go at the end of it, and you'll find those outputs. So that's kind of interesting for new users as well. If you want to know what is the power, you have to put it in the outputs of aerodyne for the aerodynamic power. And the other thing that is interesting about this simulation is I use nodal outputs. So I have axial induction, normal force, tangential force. And if you look, for instance, in PyDatView or in Python, you can see all of a sudden I have a lot of output channels here, axial induction, with a bunch of, if you were to read them, it starts with an A, which is for aerodynamics, B1 for blade 1, N001 is the first node of the blade, and then axial induction. This one is the 18th node of the blade. So you could technically plot them all. You have the normal force at different nodal location. Typically, what you want to do, you would run a long simulation, and then you'd probably average those sensors and try to look for every radial position. How does the normal force look like? And again, I'm advertising PyDatView, but you can do this with OpenFAST nodal average. That's this little menu here. You can average typically over the last two period of revolution. And it shows another table, and it gives me the axial induction as function of radius, the normal force as function of radius, the tangential force as function of radius. So that's usually, if you care about aerodynamics, or even if it's a structural dynamics, you probably want to know the bending moment along the blade. Same principle, you could do this. So pretty useful. And in that case, what I would do, you could also export the Python script that does this. So PyDatView will generate the script, whatever manipulation you do to the data, PyDatView can export the Python script that does it for you. You can choose the OpenFAST toolbox. I'm going to talk about it. It's and hopefully that runs. You can also try it. It runs it, or it fails because I don't have the OpenFAST toolbox installed. But hopefully I have PyDatView installed. I'm not sure. And then it generates basically a similar plot. It's not going to be perfect, right? It's not going to be exactly the same. But I use it when I want to prototype. I need to really, of course, I like programming, so I'm going to program my own scripts. So I don't need a GUI. The GUI is for debugging. And then once I know what I want to do, and most of the functions that are in PyDatView, like filtering, fast Fourier transform and everything, you can redo them like this. So I find it pretty useful. Anyway, case 2. Any questions about case 2? Aerodyne, any questions about aerodyne, inflow wind? Yeah. Exactly. So that's a good question. So this is all governed for the aerodyne outputs, nodal output is going to be governed by your aerodyne blade file. So you can see my blade file has 19 nodes, 19 kind of rows. So those are like how the chord and twist are defined in the aerodyne input file. That's what I had when I plotted this blade file. When I plotted the chord and twist, I only have 19 points. So then when I open the main file, and I can open it here, you can see how I have 19 actual induction output because those corresponds to the 19 nodes I have along my blade chord, my blade span. At the bottom here, I can see 19. That's the number of points I have in this data file. And yeah, good question. And if it was Elastodyne, you would open the Elastodyne blade file, which you can do as well. Here I have Elastodyne blade file. I can open it. And you can see I have 49 points. And so if I were to do nodal outputs of the Elastodyne blade moment, I would have 49 nodal outputs. Another question? Okay, we're halfway through. Question in the back, sorry. That was my take at it. I can take another pass at it. So again, I think if it is confusing as a new user, so you would have to figure out what is everything. This is the aerodyne blade file. And if you're a new user, what does that mean? You know, if you could guess, but they are documented. You would probably go to the OpenFAST documentation and you could try typing BLSPN. That was this first column that shows up here, blade BLSPN. And then it seems to pop up, and we are actually in the aerodyne documentation. So that's a good thing. And it sounds like you would have to scroll a bit until you get to it. You get to this section, which is highly hidden, 4.2.3.19.2, but that's the blade data input file, and you can read all the documentation, and the coordinate system is here. Yeah. Yeah. So it's going to depend, yeah. So that's what Jason was saying, that the fact that those files are independent. So you could do different aerodynamic shapes for the same structural data, right? If you're just trying to optimize the aerodynamics of your turbine, maybe you can just change the aerodynamic file. If it's a completely new turbine, and you'll change both files, right? You'll have new structural data, so you'll need a new Elastodyne blade file and some new aerodynamic file as well. Exactly. So that would be the output of Elastodyne. So if you open the Elastodyne output, you'll at the end of it, you'll choose what kind of output you want. And if you change your blade of Elastodyne, you'll have to change we can actually have different blades on the turbine. So you have one elastodyne blade file for each of the blade. If you change the structural and mass properties of the blade, you would change those files.
a blade mass density or
Sure. Yeah. So that starts to be a bit advanced. Today we're going to show you how to do it if you wanted to program it. Like if you want to have a script that does it. If you want to know physically how to do it, that's a bit more work. Like the WISE framework that we're going to talk about has tools to do this because they can go from structural properties of a blade to whatever OpenFAST needs. But it's more advanced. Yeah. Okay. One more question. Okay, I'll move on. Let me just keep it like this because I keep going back and forth. If you're curious, there's a case number 3 where I add the controller. So one thing you could do, I list everything on the slide. In this case, we also have 3D visualization. So for some of you, that could be interesting. So you could try running case number 3. But what I like to do is to compare the cases. I take case 2 and 3. I compare them with this program of mine that I just lost. Yeah, I made a shortcut for it, so I don't know. I compare those two folders, and you can look at what has changed. And you can see what has changed is not much. I have comp servo that has gone from 0 to 1. So now we have servodyne, the controller. And now we have a servodyne input file. And what I also changed is write VTK at the end so that I can have VTK visualization, which is, we're going to see what this is. It's a bunch of output files that we can use to visualize the turbine. So I don't know if you run the case, but I can do it for you. Main.fst. I'm in the wrong folder. That's a classic. Folder 3. Mistype. You can see it runs a bit slower. Actually, doing visualization is slow. So that's something to remember. Okay, so don't. It's nice, it's fancy to do animations, but at the end of the day, it's going to slow down your computation and create a lot of data. For this simple case, I have 100 megabyte of data generated, and that's just a very tiny case. So you can imagine how it can get big. So I'm opening the software called ParaView. You can download it, install it if you don't have it. It's quite useful when you use OpenFAST for visualization. So this was folder number 3, and you can see this VTK folder was generated by OpenFAST, and inside of it, there's a lot of things. I might as well take everything at once, take all the files at once. I need to click on apply. And I have a turbine and a ground. Okay, so that's the simulation I just ran. That's all those surfaces were generated by OpenFAST. And I can click on play, and my example is not the best in the world because I have not so many frames per second, or it's like it goes a bit too fast, but I can go step by step in that case. And you can see the tower moving a bit. Let me just go back a bit. You can see how the thrust force is making the tower go backward. It's a very low resolution simulation just because I just wanted you to try it out, okay? It can look way nicer and fancier than this. So it's just a small example for you to try out. But yeah, if you have hydrodynamics, you can also see the wave surface moving. If you have a jacket structure, you'll see the jacket. And that's going to get, the folder is going to get bigger and bigger. You can also use this for fast farm. So every turbine, if you have 100 turbines, each of them are going to export their surface, and you can see all the turbines moving with the flow visualization. You can also export planes of flow field. So you can do fancy movies like this, okay? Takes a lot of data, but you can do movies like this. Any questions about PowerView? Yeah. I think slightly beyond my power view skills. I mean, exporting meshes, that's easy. It's the same flag of write VTK thing. But then in power view, you'll have to probably use the filter that is plot on line or something like this to display on the side to display the plot. Yeah. I've never fully done it. Another question on power view? If you don't have it, download it, try it to open it, those VTK files. It's kind of fun. So I have this VTK folder, the main file. Well, we have Servodyne in here. Maybe I can point you to the most important part of Servodyne. This is the Servodyne input file. What's quite important is the DLL you're using. And in that case, I'm not using a DLL because it's a very simple simulation. But if you were to use the Roscoe controller, this is where you would start. You would go to this DLL file name and put the DLL of Roscoe here. I wanted to give you a Roscoe example, and I didn't have the time to do it. So next time I'll do it for sure. And at the top, you would say here, for instance, for the pitch control mode, right now it's 0, which is there's no pitching. But option 5 is the one you would typically use, which is where you use a DLL. Is user defined from bladed style DLL. Okay, so typically when you use Roscoe, you put PC mode, pitch control mode equals 5. This is the generator control. You would also set it to 5 to say, hey, I want to use the Roscoe controller. Okay. And then a lot of the inputs don't matter anymore because everything is going to be handled by the DLL. In that case, I just have a generator torque. I don't know if there's some physics we can go through. I think the rotor speeds kind of stabilize a bit. So there's a balance between the aerodynamic torque and the generator torque. So I also output at the end of my Servodyne file, same principle. In the out list, I say I want the generator power and the generator torque. And then I can see that I have those two channels here in my output file. Do I have the aerodynamic torque? I have some rotor torque. That's probably the one from and then yeah, that's the one from Elastodyne. And the rotor speed is kind of reaching some kind of equilibrium. It takes a while, but it reaches an equilibrium because you have some generator torque on the other side that's kind of, in that case, we are in region 2 of the turbine. So that's below rated. And a simple generator torque is just going to follow, it's going to be proportional to the square of the velocity of the rotational speed. So that's why in that case, the two curves look very similar. Potentially, I could verify this. I could, in pilot view, I can add a channel, which is the rotor speed squared. I can call it rotor speed number 2. It's not RPM anymore, but okay. So I can take this as an x-axis. Instead of time, I could take the rotor speed squared, and I plot the generator torque as function of it. And you can see that it's linear. I could also plot it as function of rotor speed RPM, and then it should be quadratic. It's hard to see here. Because probably the slope is very, very small. I would need a longer simulation. But anyway, things you can do with it. This is just things you can try, things you can experiment to see if your controller is doing what you think it is. So that's why, yeah, that's why I'm showing you this. Yeah, that was the idea behind case 3. Any questions about this? I'm using Servodyne with the very simple option that is a simple generator torque that is tracking the optimal CP, if you know about this. If there's no question, let's see. 214. I think I'm not going to go through those examples with you, but briefly I'll mention what they are. Case 5, it's nice if you want to learn about how to do turbulence simulation, okay? So in the binaries I give you, in the Google Drive, I give you a binary that is called turbsim.exe. That's what we use at NREL to generate turbulent boxes. So maybe I'll do it on the fly live with you. I have this turbsim.exe. Again, what I would do is I would just put it into the folder, folder 5. And what you'll notice is I have those turbsimbox.inp. Actually, for Windows users, I'm going to give you a hack, something I didn't tell you before. If you're a Windows user, if you want to run this OpenFAST simulation, you can take your main file and drag and drop it on OpenFAST, and it's going to run it. In that case, it's going to crash because the turbulence box is not here yet. Yeah, sometimes that happens. You can see it crashed on me, and the error message was very hard to read, but it was because the turbulence box is not here yet. So what you can take is, this is an input file of TurbSim, which is the turbulence generator of OpenFAST. It has a bunch of parameters. Again, it takes a lot of learning. Some of the important one is how many points you have in your turbulence box, what is the size of your turbulence box, and of course, very important is what kind of turbulence you have, what kind of turbulence model, standard deviation of the wind speed, and also do you have any shear in your box. So for now, let's just run this input file on TurbSim. So I can do the same. I can drag and drop it. And it generated a BTS file, which is a TurbSim box. It has the wind speed at every node as function of time. And again, PyDatView can show it to you. So that would be my first reflex, is to put it in PyDatView. First input that PyDatView gives you is the vertical profile. So in TurbSim, you can introduce shear in your turbulence box. That's something that manned boxes don't do. But in OpenFAST, you can have the shear profile, the variation of wind speed with height, in your turbulence box. So usually we would flip the X and Y to show wind speed as function of Z, like this, right? So we can see we have some kind of parallel. And if I were to open the TurbSim file, I could see this was defined here. Some kind of reference velocity at 90 meters. So I better check that at 90 meters, I have 8 meters per second. So I'm checking on the fly at 90 meters. I do have 8 meters per second here. I can probably mark it, but something like this, 98, perfect. If the font is too small, you can increase a bit the font. So that would be one thing to check. If you have a turbulence box, is there shear in it? PyDatView can help you, but you can do the same with Python as well, no problem. You can check also, what is your standard deviation as function of height? What is your turbulence intensity? That's a quick way to get those information out of this. You can look at the midline. So at the middle of your box, what is your velocity looking like? Okay, so as function of time, this is just a 1-minute simulation, so pretty small. But you can see UVW, you can plot those 3 components of the velocity, maybe on top of each other if you want. And of course, the V and W, those are like the transverse wind speed. They tend to have a 0 mean. So something to double check. Here, the mean speed is about 8, the mean wind speed at the middle of the box. You have this table at the bottom that tells you the mean standard deviation. You can also compute the damage equivalent load if you had a load time signal. You can compute the TI on the fly also here. You have a bunch of channels. If you click on this little thing here, you can choose all kind of different channels that you want to compute on the fly, like damage equivalent loads, and it adds more columns here. So now I have the TI also on the fly. Anyway, that's just, you can also do 2D plots here with TurbSim. You can visualize your box with at different heights, different location. Okay, that's just, quality checks. I have also this file info tab in PyDatView. So I have the 1D plot. That's the the one you would typically use for simple time series. I have the 2D plot for those kind of plot that are a bit more fancy. And I have the file info plot where you just click on your file. And by default, it's just going to tell you some useful information about your file. For instance, what is my z-axis? It goes from 12.5 meters to 167. So I have 21 points, which is exactly what we had in this input file, 21. So it's a good quality check. It tells you the size of your field, the size of your time. It tells you if it's periodic, ID 8. So you would have to be a super user to know this, but if the ID of a turbulence file is 8, it's a periodic file. Anyway, so now I have generated, so that's how you generate the turbulence box with OpenFAST. You need to learn about this TurbSim input file. You run it through the TurbSim executable. And now I can run this OpenFAST simulation. And it doesn't crash on me because it's reading the input file, the turbulence box file. You can see it's already slower compared to our other simulations because it's reading the turbulence file. And now our time series are going to look a bit more interesting. I failed. You can see how this is exactly the same wind speed as I was showing you. That's the wind speed that is reported by OpenFAST, though. And if I look at the power, well, there's still there's oscillations from the turbulence in it. It's just a small time series, so we don't see too much oscillations. But you could plot the spectra of it and try to see what are the frequencies in my system and things like this. Any question about all of this? Yeah. Yes. So I would use those channels not for the wind speed, of course. Like I would use those for the loads. So for instance, the tower bottom, I would read the damage equivalent loads for m = 3. Okay, so this is a load time series in kilonewton. I would run it through this. I'm not going to compute the damage equivalent load. I can compute the damage equivalent load of wind speed, but it doesn't mean much. Okay, yeah, and that's all. It's just the algorithm. It's just an algorithm, so it works. But as an engineer, you look at whatever damage equivalent loads at the bottom of the tower, for instance. It's nice, and I guess yeah, exactly. So everything is that's why we have those workshops as well. I mean, for new users and for more advanced users. Any other question? Yeah. So Flores is just a different tool. What do you mean that you? So yeah, I mean, the BTS file, I think it's mostly OpenFAST that uses it, but the other way around, we use output files from, for instance, the man box, right? So OpenFAST can use files from the man box. And those BTS files that we use here, they can be used for FastFarm as well. So it's not like but the industry they also have readers for BTS files because they know a lot of people use OpenFAST. So yeah, but it's mostly for those kind of engineering tools. Yeah. Yeah. Okay, so I have more examples. Yeah, things are oscillating. I'll invite you to look at the slides. I also have an example for a monopile. Now we're going to use the subdyne module. So you're going to have a subdyne.dat input file. And you could visualize the mode shape of the monopile also using this tool. I would need to go to that folder. You would run your simulation just like we just did for this example, and you can ask Subdyne to generate the mode shapes of your structure. In that case, it's just a monopile, and you can visualize your mode shapes. So for monopile is not too interesting, but still, you know, it's nice to understand. If you are new to modeling substructures in OpenFAST, we have what we have 6 degrees of freedom at the joint between the tower and the support structure. Jason mentioned them, those 6 degrees of freedom that we move the tower with. And what happens is the 6 first modes of the substructure are going to be the ones that are going to give you those displacements. We call them Gaussian modes. They are constrained modes that they make sure that the first mode is purely translation in X. The first mode, so they are constrained to do exactly this. So if I look at the first Gaussian mode of my monopile, you can see how it's a pure translation. It's not the finite element mode. It's a bit different. It's a constrained mode such that the monopile moves purely in the X direction at the top. So it's a good way to visualize your modes and make sure they are as you intend. And then when I reach the other internal modes, what OpenFAST called internal modes or Craig-Bampton modes, those are the opposite. They are such that the interface is fixed, but internally the structure might move. So yeah, that's how you would visualize them. So monopile, jacket, that's how you see them. Yeah. Yes, yes. That's one of the limitations of Subdyne, is the modes are computed standalone, as if there was no top mass. But Subdyne will then, because you have this mode that you're going to have an internal mode, and it's actually pretty important. That's one way to check it. You want to have one Craig-Bampton mode that accounts for the squashing, the gravity kind of squashing of the structure. So that would be a mode where the structure sinks in. And you need this mode because otherwise your response is a bit fake. Yeah, another example with the jacket. And here I have also, not only do I have so for instance, the first Craig-Bampton mode of a jacket, maybe it's hard to see the first Gaussian mode of the jacket. Sorry for my visualization here. But it's a pure translation in one direction. But if I look at the first finite element mode, it's actually in the other direction. Let's just look at that one. I have translation and rotation. So you can see how the structure rotates at the top here. That's the finite element mode, but the first Gaussian mode is a pure translation. Hopefully you can see this difference. There's a way to slow this down a bit, but anyway. You most likely use that tool in the process of building your model. Yeah. That's only for Subdyne. Hopefully we're going to integrate this into the other tools at some point. Let me go. So yeah, you have those cases. I'm not asking you to run them because now you're getting familiar with it. But at least you have them. So if one day you want to model a structure and you need to do turbulence, you have the executable, you have an example of input file that works, so you can get started. So now I want to go through when you're alone and you need help. Okay, what do you do? Obviously, we have some documentation. It's painful to read any kind of documentation, but we try very hard. Okay, we're making progress. I think it's getting better and better as we mature the software. So yeah, go in the documentation, search for an input. That's a good start. You can also try to read all of it if you want, but if you just care about the aerodynamics, start with the aerodyne documentation, for instance. Not everything is on the internet. So, I mean, everything is on this website, but sometimes we have PDFs also for the things we haven't converted yet to the read the docs. I mentioned earlier a quick start. If this was not enough, if this workshop was not enough, there's another step-by-step quick start with some input file that you can follow. You can ask for help on the forum that we have, the annual forum, where you'll have Jason that dedicates a lot of his time to all. Exactly. Yeah. Well, so head down for Jason. Because it's not like he's being paid to do this. So that's a lot of his free time. So yeah, definitely thanks to Jason. Obviously we use GitHub, so we try also to give feedback if you have issues on GitHub. This is also the place where if you implement something in OpenFAST, this is the best way to communicate. But as Jason mentioned, if you want to implement something in OpenFAST, it's always best to tell us before, because maybe we want to program it. We are working on it, and so we don't want to have conflicts. So we can collaborate early on. That's the best. Instead of you telling us, "Hey, we did this," and now we're like, but we already did it in a different way. And so always contact us first. We are always happy to receive new contribution, but as early as possible. Okay. One problem you're going to run into is the fact that the input file changes with different version. What we try to do now with the version numbers, I think it's standard in the software industry, is like the second digit. So between 3.4 and 3.5, in theory, there's no change. Well, no, sorry. There could be a change of input file between 3.4 and 3.5. But there won't be change between 3.5.1 and 3.5.3. There won't be any change. But between 3.5.3 and 4.0, there's going to be a lot of changes. Okay, because not only am I changing the second number, but I'm also changing the first number. So you could expect a lot of changes. And as Jason mentioned, 4.0 is coming very soon. And I'm actually happy it's not here yet, because I would have to change all the files for this workshop. And but I'll do it. I'll do it. It is painful. Yeah, and 4.0 is going to be a bit annoying, especially on the aerodynamic side. I provided a Python script that converts Aerodyne file from 3.5 to 4.0. So you can run the Python script and it does it for you, because there's a lot of thinking for the Aerodyne change that are coming. All the other inputs, it's just you add new lines, it's easy. But for Aerodyne, it takes some thinking. Anyway, so we document it, of course. So this is the link you would probably want to check. You'd click on that link and see what happened between version blah, 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 and blah, blah, blah. And we usually have a table that tells you what has changed. What you can also do, what I like to do is I would go to that website, which is where we put all of our tests. It's the R test website of the regression test of OpenFAST. So those regression tests are running each time we do changes. So they are always up to date. And I can show you how you could do it. You just go on this website. My computer always complains when I change from full screen on it. So you would go on the OpenFAST regression test GitHub page. And then what you can do is choose a tag that corresponds to the version you want. So soon there's going to be a tag for 4.0. Right now it's in dev. So I could go on dev, or imagine it's like the tag 4.0. And then I can look at examples of input files, for instance, for OpenFAST. I have the 5 megawatt turbine. And here I'll have a lot of files, and I'll probably have I thought I put an example one for the Aerodyne. I don't have one for Aerodyne, but I have inflow in. I could click on it, I could download it and compare to my file and see what's the difference. I would actually download the full folder at once, and then you can compare and see what's going on. So for instance, I could look at the Aerodyne file here, and well, a lot of things have changed, but let's just say the nacelle. Now we have a whole section about the nacelle that you don't have in your Airdyne input file. We have the nacelle drag. We have some hub volume for hydrokinetic turbine if you want to account for buoyancy. So all of this is new, and you'd have to add those lines to your input file. So the best way is to download this file, and then you have an example that works. So just something to watch out for. We are aware this is extremely painful. But yeah, that would be the path forward if you want to figure out. You can also look at the table. This is what's coming out for 4.0. Those are, it tells you for Airdyne, there's a bunch of, for Airdyne actually it's listed on the right. But for Fast Farm, you can see there's a bunch of new lines at the end. For Hydrodyne, yeah, this is the kind of changes you might have to go through for 4.0. Any questions about this? Tools, I think I gave you an overview of PyDatView. This is the tool I'm developing. When I was working at NREL, I would use it 20 times a day. I can give you more demo, but yeah, you can compare different output files. I think that's how I use it a lot. You run 2 simulations and then you compare the output files. You can do those nodal outputs. You can do FFT, Fourier transform to see what are the peaks in your signal. So it's very nice for quick and dirty debugging. So I highly recommend you use it. Yeah, you can plot the airfoil shape that you use in OpenFAST. I'll skip it. Then another tool, when you want to get a bit more into programming, we have the OpenFAST toolbox. So that's also another one that I mostly developed. Who knows how long it's going to last? It's probably slowly being replaced by Wise. But I can show you a couple of examples. So the good thing is PyDatView generate the code for you for the OpenFAST toolbox. So then if you download the OpenFAST toolbox, it's a Python package. You install it on your machine, and then you can take the scripts from PyDatView and already get started and do some post-processing. So I give you the examples of a couple of examples that I'm going to go through in this folder called demo OpenFAST toolbox in the package. And first example 1 is how to read an Airdyne file, and you change it. Let's say you want to change the density. You could do it, of course, by hand, or you could simply, it's just 4 lines of code. You read the input file for Airdyne, you activate the aerodynamic of the tower, the aerodynamic forces on the tower, you change the air density, and then you write it to another file. Okay, so pretty simple. So for changing the blade, I think I have another one. It's probably the next one. To read an output file, similar syntax. Okay, so you just read an output file, and then right away you can plot something like the rotor speed as function of time. Again, 3 lines of code as soon as you install this toolbox. The other examples I give you is like, yeah, plotting the Airdyne blade, the chord as function of radius. Again, this is, you just open the Airdyne blade file, you convert it to a pandas data frame. If you know what that is, it's just a table. And then you can plot the blade span as function, the chord as function of blade span. And you could modify it. You can open this file a bit similar to this. I would just open the file and you could change the chord. You could change the chord and then write it to another file. Okay. You can also read a TurboSim box, just like PyDatView. Whatever PyDatView can read, the OpenFAST toolbox can read too. So this is where you could make your box periodic. You could have a wind field that is not periodic, and maybe you could flip it, which is not nice in theory for turbulence. If it's a proper turbulence box, you probably don't want to do this. Like, you know, the vortex structures probably don't want to be flipped. But you could do this. You could add shear. You could create your own box this way, or you could plot time series just like a PyDatView was plotting the shear profile. You can compute the shear profile and things like this. So those examples I provide you, all of this is in the folder for the demo. If you want to read the polar data and make sure, that your linear region corresponds to is well calculated, you can also read a polar and then compute the linear region and plot everything together. And what is my last example? An example that I think is very useful is what I was showing you, the axial induction as function of the span. Or it could be the blade bending moment as function of span. The toolbox can compute this for you, and it does it in a way that I think is good and that should be done. We average by period of revolution because we don't want to just take the mean of a signal. We know our signals tend to be periodic. So it's good to average on a full period. If you average if you average sine on a full period, you should get 0, right? But if you average just on half a period, you're not going to get 0. So that could skew your results if you don't average properly wind turbine output channel. So this will do the output properly, the average properly, and it will also open all of those 19 outputs and make them averaged all of them, and then you just plot them as function of radius automatically. And also another thing it does automatically for you, it's going to figure out what is the radial position of each of those nodes. So it's reading the Aerodyne blade file, making sure you have the right radial position. If you were to do this on your own, I'm telling you, it's going to take you some time. So I recommend using the toolbox. This is an example, a bit more advanced. Again, if you want to run a lot of simulations, this is example 7. It's running a parametric study. It's changing the wind speed, the RPM. It stores everything into a Python dictionary for different RPM and wind speed. You define a case name. And if you run this script, it's going to basically generate the OpenFAST input files for all those wind speed and RPM. And then it can also run the OpenFAST files and post-process them. I can maybe do a small demo, but you have the script. You have the script somewhere. I have no idea. Yeah, I'm in the wrong folder. I'm in the old package. Okay, that's okay. But it should run. It actually runs in a few seconds, this example. Yeah. So I just made a mistake. I'm running my old workshop files, which is a bit of a bummer. Yeah, and I was in the okay, that's why. But yeah, it's going to store everything OpenFAST toolbox, and yeah. So yeah, you see it ran pretty fast. It ran a couple of wind speed, and now it's showing me the power and the thrust coefficient for all of those different wind speed. And I think it generated this folder outputs. No, it generated this folder parametric. Yeah, parametric. And I have basically all of those files, case 1, 2, 3, 4, 5. And each of them are different OpenFAST files. I can compare them. And you see the only thing that's changing is the Elastodyne and inflow wind files. So again, this is something that would be painful to program. So to generate all of those input files, and you can compare 2 inflow wind files, and you see they have different wind speed. Basically, that's the only change between them. Yeah. But it's a good learning experience, right? Isn't it? So yeah, you can do this with few lines of code like this. You have those examples in the package, and yeah, you can find more online. Then I think it'd be worth for the last time we have is all of us trying to run AC/DC. It's a new software that is generated that has been written by our colleague Derek Slaughter, who joined NREL 2 years ago now maybe, and it allows you to do Campbell diagram. So hopefully you have this executable. It was in this binaries folder, and you can try running it. And we're going to need the folder number 12. Sorry, I just have too much stuff going on at the moment. So, actually, let's just, so you have this ACDC V06A. If you run it, it shows something like this. Typically, you would create a new project. You can save it anywhere you want. I'm going to save it where I am. What matters is then you go to the next tab. There's a model tab. This is where you're going to have to import what we call a template. And I needed a template also for generating all those simulations. Those are like a good set of input files. You better make sure it's a good model that works well and has all the parameters you want. And you're going to import the .fst file. This is where I made a mistake because I'm not working on the right package. So you navigate to the package folder simulations, and I have this folder number 12 ACDC. And then I have a template folder, and I have the main.fst. Sorry, so that's a lot, but yeah, it's in the simulation folder, 12 ACDC. In the template folder, you have, I would take the main file from OpenFAST. And then it basically opens all the input files, and you could change them. You could change those input files. You could check them at least for sanity, check the important one. And one very important one is the out format. When you do linearization, that's actually feedback for Derek. It would be nice if we actually hard code the change, but make sure this is a high resolution output format. So by default, OpenFAST has only a few digits. This is how many digits OpenFAST use when it's writing files. We want a lot of significant digits because linearization takes a lot of, it's very sensitive to numerics. You could change it here. I prefer to change it in the template and then load the template. Then you would go in analysis. So this is where you want to do a Campbell diagram. So you want to check the linearization. You want to linearize your system at different operating points, different wind speed, different RPM. Actually, I have a step-by-step. If this is going too fast for you, I have a step-by-step case here. I'm just going a bit faster, but I show you how to run ACDC around slide 47. And I really highlight where you're supposed to click, how it's supposed to look like, what are the inputs you're supposed to go through. But typically, you would maybe change the name of your simulation. You say, hey, I want aerodynamics. And then you would have to import the conditions. It's a CSV file typically that tells you what are the wind speed, RPM, and pitch angle of my wind turbine. So this is how it looks like. This is what the data that I have in a CSV file that tells me as function of wind speed, my wind turbine is going to pitch. That's the blue curve. This is how the controller will pitch. In green, I have how the controller will set the rotor speed. So typically when you design a turbine, you know those, after some iteration, you know what is the pitch and the RPM of the turbine. And now you want to know what are my system frequencies, what is my damping for everything, and what are my mode shapes for different operating condition of my turbine. That's what this tool is all about. And I think the crosses here that you see on this plot are the ones that were in the CSV file. And the circle are the ones that you can specify. So here, when I say I want to cut in at 5 meters per second, and I'm going to go all the way to 25, and I'm going to use only, let's say, 5. I can do 8 points. I don't know. 8 operating points. So now those are like the blue, the circles. They're a bit hard to see, but those circles are my 8 simulations I'm going to run. So ACDC does linear interpolation between my my operating points that were in the CSV file. Then you go on evaluate, and then you choose how many computer CPUs you have. And first you need an OpenFAST executable. So you use your exe, make sure it works. It tells you the version. And it's going to run those simulations. In that case, it's pretty fast. Sometimes it crashes. If you use the wrong OpenFAST version, it's going to crash. So you click on the log file and it tells you, hey, I crashed because I couldn't find something, or the input file is not good. But in that case, it ran pretty fast. And you can check the results. The baseline name is called base. You can post-process the results. You generate the Campbell diagram, and that's it. So now you have, as function of wind speed, I have 8 data points because I chose 8 simulations for starting from 5 meters per second to 25. This is the natural frequency. This is the damping for the first few modes of my structure. And it doesn't tell you which mode is which. So for instance, I have modes at the bottom here. I can click on one of them. It has some damping in it. And then once I click on one of the modes, it shows me some more menus at the bottom, and I can say visualize. Takes a bit of time, but then it generates those visualization for me. It's not interactive. I cannot click around, but it shows different views. And then as an engineer, you can say, well, this modes look like it's the tower fore aft mode, because it looks like it's mostly the fore aft motion of the tower. And you can check for the different operating point. This was like at low velocity, and you can look around for all the different velocities. It looks more or less the same. Okay, and then you can confirm that it looks like a fore aft mode. Then this mode, I don't know which one it is. I'm going to click on it and do visualize line modes. Now that looks a bit different. The motion is a bit tiny, so what I can do is I can change the scale here to, I don't know, 200. Let's go crazy. And you can see it is a side-to-side mode of the blade. It's an edgewise mode of the blade. It's not collective. And then you can try to think if it makes the turbine goes, if they go in the order, I think it's a progressive one because it goes in the same order as the rotation. It's blade 1, blade 2, blade 3, blade 1, blade 2, blade 3, I think. But yeah, so this is our visualization tool for. So what's going on behind the scene is OpenFAST does a lot of linearization of your model. Okay. And if you were to look at the folder I called my project, it generated a folder case 1. And in this folder, you'll have all kind of OpenFAST input file.fst files. I have all my 8 simulation file here. So you can check, you can double check what happened. And it generated 1 lin file for each of the simulation. A lin file is a linear model. I'm going a bit fast here, but you could open it if you want. You can read them with PyDiveView with the OpenFAST toolbox. No problem. And you can extract yourself. What's important usually for engineers is the A matrix. That's the state space matrix from state to state, from state derivative to states. And you can compute the eigenfrequencies of this A matrix yourself, and you'll find that it's similar to what you're going to get from ACDC. So that's what's going on behind the scene. It's a lot of OpenFAST simulations that are linearized to generate this diagram. The dashed line, good question. Those are like the RPM. This is the 1P, 3P, 6P, 9P frequencies. So as an engineer, you want to look at, well, what happens when one of my mode crosses one of those frequencies, because it can create excitation. Doesn't mean that it's going to be unstable, but it can excite my system. Yeah. More questions about ACDC. I know it was pretty intense, but you have all the files. You could do this. You can reproduce it. And like I said, in the in the slideshow, I give you a step-by-step for where to click. You know, like, oh, click on this, then you'll see that this works. Then click on this, then click on the logs, click on this, that. So hopefully, you know, you can redo it at home if you want to do linearization. Any questions about this? Yeah. I don't think so, but you can use a V-clip. I don't know. That's the software I use on Windows. You can just screenshot your screen. Yeah. Actually, I kind of went ahead of what I wanted to say, but AC/DC, okay. Once you get advanced users, you can use WISE to generate all kind of simulation file and things like this. This is beyond the scope of this workshop, but when you want to run DLCs and do a lot of simulations, I think this is where you want to go. So WISE and Roscoe is when you want to have a controller that is easy to use. In the case, you'll find examples for OLAF. I think it's fun also to try OLAF. The big thing, so OLAF is our vortex method code. So if you have vertical axis turbine, if you want to do something better than BEM, you can try it. What's very important is read the guidelines. Okay, so I give a script. I also give it in your example here in folder number 9. There's a script that you can run that tells you, hey, use those parameters for OLAF. And that's really going to help the quality of your simulation. And so in your example 9, I have a script called params.py. And it's going to tell you how big your near wake should be. Let me get to a figure to explain. This at the top here, I have an example of simulation that is poor. Because basically, if you look, there's VTKs that can be generated by OLAF, and you can see that your wake is very small. And of course, what happens is you end up with a power coefficient that is super high in your simulation. That's because your wake is too small. And so if one of the parameters that is important for OLAF is how long is your wake. And so you could, this case 9, the idea behind it, if you run it, is you run the Python script, it tells you how to change your OLAF input file. You change the OLAF input file, you rerun the simulation, and then at the end, you can see that it takes time, but the power coefficient goes to some more reasonable value. Your wake looks longer. And yeah. The other parameter that is tricky with OLAF is what we call the regularization. So those are the wake reg factor. I lost my, okay. Those wake reg factor and wing reg factor. And I have recommendations also in the guidelines on how to do this. So yeah, just run those examples. I think I'll stop very soon. I'd rather have questions now. Yeah. You'll also find case 10 and 11. Those are simple linearization. If you don't want to use AC/DC, if you want to just linearize the structure to figure out what are the natural frequencies of the blade in vacuum, you would do it manually. And to linearize manually, you need to change the .fst file of OpenFAST with setting linearize equals true, and then you get a .lin file with a A matrix that you can open yourself. But otherwise, you would use AC/DC, which is easier. So that's it. Yeah, any question about OLAF or linearization? Yeah. Yeah, exactly. Yeah, more questions? You, did you create a new project? Yeah. Don't try to open anything. First, you create a new project. No, but the AC/DC also saves the whole project into a JSON file. Don't try at first. Always create new projects. It's easier. And the new project, you just save wherever you want, and then you need to open a main OpenFAST file. Other questions? So I know this is a lot, but so I think the good thing is you have this package folder with all those Python examples that you can try. Remember them. You also have all those OpenFAST cases that I didn't go through, but you can try them. If one day you want to use a controller, you can go back to this and see how did they do the controller. If you want to run OLAF, go back to the slides in this example. If you want to run AC/DC, the slides detail a bit how to use it. So it's really to give you pointers of where to find help and where to download things. I think it's time for a break, right?